Hey everyone, welcome back to the series. In this video, we're going to build the neural network class, and we'll be using the Layer.hpp and matrix.hpp files we created earlier. We'll walk through how to connect layers, initializing the weights, and set out the forward path so our network can make predictions. Let's get started. We begin with the header guard. Hash fndef neural network underscore hpp and hash define neural network underscore hpp, and we close it with hash endif. Then we include the necessary libraries. Hash include vector to handle dynamic arrays, hash include std_except for throwing exceptions, hash include cmath for mathematical functions like square root, the sqrt function, and hash include chrono for measuring training time. Next, hash include layer.hpp, and the last one, hash include matrix.hpp. Now we define our neural network class neural network. Inside the private section, we define two important members: private std vector layer layers, and the next one is std vector matrix weights. Layers will store all layers in our network, and weights will store the weight matrices between the layers. Now we're going to add a private method, void connect underscore layers. This method creates weight matrices that connect each layer to the next. Inside the method, we loop through the layers. For size underscore ti equals 0, I less than layers.size minus 1 plus I. We say layers.size minus 1 because we're connecting each layer to the one that comes after it. So if we have 5 layers, we only need 4 weight matrices between them. And then we create a new matrix for each pair of layers using the inplace back method like this. Weights.inplace underscore back, and we pass in layers square brackets I dot size and layers square brackets I plus 1 dot size. Now let's add a method called initialize weights to set up the weights with random values. Void initialize weights. Inside the method, we start with looping through all the weight matrices and initialize them with random values. And here we say for auto reference ws colon weights, and inside the loop ws dot fill random. After filling the weights with random values, we scale them using heat initialization. ws times equals sqrt, and we pass it 2.0 divided by ws.getRows. This technique is called heat initialization. It's great for networks using ReLU activation functions. It helps maintain a consistent variance of activations across layers, which leads to more stable and efficient training. This reduces the risk of issues like vanishing gradients or slow convergence in deep networks. The formula is straightforward. We take the square root of 2.0 divided by the number of input neurons, which corresponds to the number of neurons in the previous layer. We use ws.getRows because it returns the number of inputs feeding into each neuron. Next, in the public section of our class, we create a constructor, public neural network, and it takes const std vector layer reference network underscore layers, and we assign network underscore layers to the layers member variable, colon layers network underscore layers. Then inside the body we call connect layers and initialize weights, connect underscore layers and initialize weights. Now we're going to add the forward method that performs forward propagation through the network. std vector double forward, and it takes a vector of doubles as input. Const std vector double reference input, which represent the data we want to feed into the network. Inside the method, first we check if the input size matches the number of neurons in the input layer. And here we say if input.size is not equal to layers square bracket 0 dot size. If the sizes don't match, we throw a runtime error. Throw std runtime underscore error, and we pass in this message: input size mismatch. Next, we assign the input vector to the activations of the input layer. Layers square bracket 0 dot a equals input. The input layer simply outputs what it receives, passing these values forward to the next layers during the forward pass. Now we loop through each layer to perform the forward propagation. For size underscore t l equals 0, l less than layers.size minus 1 and plus l. Technically, since weights connect layers, we're really looping through the weight matrices. So you could also write l less than weights.size instead of l less than layers.size minus 1. But here we keep it as layers.size minus 1 for clarity, because we're thinking in terms of layers rather than weights. Now, for each neuron in the next layer, we compute the dot product between the current layer's activations and the corresponding weights. Essentially, we're calculating the input to the next layer's neuron, which will be used to compute its activations. So we say for size underscore t j equals 0 and j less than weights square brackets l dot get calls and plus j. For each neuron in the next layer, we start by initializing a sum variable with its bias value, like this: double sum equals layers square brackets l plus 1 dot bias square bracket j. Next, we loop through each neuron in the current layer to calculate the weighted sum for the next layer's neuron. For size underscore t I equals 0, I less than weights square brackets l dot get rows and plus I. And here's the weighted sum plus equals layers square brackets l dot a square brackets I times weights square brackets l and inside parentheses I comma j. Then we store both the pre-activation value and the activated output for each neuron in the next layer. And here we say layers square brackets l plus 1 dot z square brackets j equals sum, and layers square brackets l plus 1 dot a square bracket j equals layers square brackets l plus 1 dot apply activation, and we pass in sum. Finally, after processing all layers, we return the activations of the last layer, which is the prediction of our network. Return layers dot back dot a. Next we have the predict method, which takes an input vector and returns the network's prediction. std vector double predict, and it takes const std vector double reference input, and it will return forward, and we pass in input. This method is optional, but I want to have it. That's all for this video. We covered initializing weights, performing the forward pass, and even added a simple predict method. In the next video, we'll create a file called log.hpp, which we need before starting to build the train method in our neural network class. If you found this helpful, don't forget to like and subscribe, and I'll see you in the next video.